This is Chrysoula Stathakopoulou, and in this presentation, we will discuss about fairness in total order broadcast and how to achieve it using trusted execution environments. This is a work in collaboration with Signe, Rüsch, Marko Brandenburger, and Marko Vukolic for the proceedings of SRDS 2021. Let us imagine a stock exchange service. Clients buy and sell stock via a broker. Such systems in reality are very complex, and most importantly, they are centralized and require trust in certain parties, like the broker, for instance. Luckily, today we have blockchain systems in the world, and we can leverage blockchain to build a distributed stock exchange service among parties who do not necessarily trust each other. Clients can now transfer ownership of stocks in a peer-to-peer fashion, and no broker fees are required. To achieve this, each party involved can now run a blockchain node. Client transactions form a chain to which we will refer to as the ledger. The ledger is replicated to all nodes, and a consensus protocol is in place to ensure that all ledger replicas are identical, making therefore the ledger immutable. This makes the consensus protocol the core of the system. We will, in particular, examine Byzantine fault-tolerant total order broadcast protocols as consensus protocols, as they have certain good properties. They are resilient to malicious nodes, they have low latency, high throughput, and fast finality. Similar to the stock exchange use cases include, but are not limited to, ICOs, bidding for domain names, even gambling services. But we will stick to the stock trading example for the rest of the presentation. Let us introduce our client, Alice, who submits a transaction to the system. The transaction goes through total order broadcast, and it is assigned a unique sequence number. We use the sequence number to append the transaction to the ledger. Unfortunately, things can go wrong. Let us assume that Alice wants to sell a big number of stocks of some e-vehicle company. Or imagine that Elon Musk wants to sell his Tesla stocks. One of the nodes in the system colludes with some other client, let's call him Dave, and informs Dave about Alice's transaction once Alice submits her transaction to the system. Dave, who fears that if Alice sells stock first, the e-vehicle stock price will drop, creates his own transaction to sell stock and also submit it to the distributed stock trading service. If now Dave's transaction is added to the ledger first, it will cause e-vehicle stock price to drop, and it will be Alice who sells her stock at a lower price. We refer to this as a front-running attack. Now, why is such an attack possible? Because in Byzantine fault-tolerant system, total order broadcast cannot guarantee for Alice's transaction that Alice's transaction will be added to the ledger first. And we want to enhance, therefore, total order broadcast with a property to prevent such front-running attacks. Luckily, such a property exists in literature, and it is called input causality. Input causality guarantees that for any transaction R1 that causes some other transaction R2, transaction R1 will be always added to the ledger first. In our example, in particular, Alice's transaction with input causality would be always added to the ledger first because it was a transaction that caused Dave's transaction. How to achieve this? Basically, we have to hide the Alice's transaction content to prevent any malicious node from acting on it. Only after Alice's encrypted transaction is assigned the sequence number can we reveal its contents, because now the order in which it will be added to the ledger is defined. We are aware of two solutions that provide input causality for total order broadcast. The first is a threshold encryption scheme. In this scheme, all nodes are equipped with a private key share, and the client uses a public key corresponding to those key shares to encrypt the transaction. Once the transaction is ordered, the nodes will use their private key shares to create a decryption share. The nodes exchange and combine the decryption shares to reveal the contents of the transaction, which can now be added to the ledger. However, this solution has some drawbacks. First of all, it requires a distributed key setup. This distributed key setup requires either a trusted third party or a distributed key generation protocol to establish the key shares among the nodes, but such a protocol, as we know, has high message complexity. The decryption share combination requires an extra round of communication after total order broadcast. Moreover, the cryptographic operations that are done for threshold decryption are computationally expensive and depend on the number of nodes. Finally, the nodes order an encrypted transaction and they do not know its contents, which they cannot validate before ordering. Therefore, malicious clients can leverage this to waste precious cycles of total order broadcast by invoking ordering for garbage. To tackle the inefficiency of the threshold encryption scheme, Duan et al. Suggested a simple commit reveal scheme. In this scheme, Alice creates a cryptographic commitment of her transaction and first sends this commitment to the network. The nodes order the commitment of the transaction, and then Alice sends her actual transaction to the system, where the nodes run again a total order broadcast to associate the transaction with the sequence number in which the commitment was earlier ordered. The transaction now can be added to the ledger with a new sequence number. However, this solution has still drawbacks. First of all, as we saw, it requires 2 rounds of total order broadcast. It is only possible to validate the cryptographic commitment of the transaction after the actual transaction has been submitted to the system, opening again the surface for submitting garbage to the total order broadcast. This solution is moreover not live with malicious clients without some strong synchronous communication, because a malicious client can always delay the disclosure of the transaction and therefore delay the progress of the system infinitely. The client identity, moreover, is required to associate the commitment with the transaction and is leaked. Now, why do we care about the client's identity privacy? Consider again the previous example, where now Alice has hidden the transaction contents, but the associated identity to the transaction is visible. Dave, as previously, finds out about the transaction of Alice, and he fears that Alice is going again to shell stock. Again, we can imagine that Elon Musk is about to perform a transaction, and we fear that Elon Musk is going to sell all his Tesla stock without even knowing what his transaction includes. As previously, Dave submits his transaction to the system, and if it is added to the ledger before Alice, Alice's transaction will result in selling her stock at a lower price. We want to enhance total order broadcast with yet another property on top of input causality to prevent this front-running attack, and we call this property center obfuscation. Center obfuscation requires that for any 2 requests, R1 and R2, associated with different identities, a function of the 2 pairs is indistinguishable by some external adversary before they are ordered by total order broadcast. The combination of input causality and center obfuscation is called fairness. Our solution, FAIRY, is adding the fairness properties to total order broadcast. The key idea is to leverage trusted execution environments to add fairness in a modular and efficient way to any total order broadcast protocol. In a nutshell, we equipped our nodes with a trusted execution environment, and we leverage this trusted execution environment to decrypt the contents of Alice's transaction before ordering, as well as to provide the nodes with Alice's transaction after ordering. Trusted execution environments, such as Intel SGX, allow us to do this because of their following properties. First, trusted execution environment allow an application to run in an isolated context known as enclave in SGX technology. This guarantees the confidentiality and integrity of the application and its data. It also prevents even unauthorized access by higher privileged code or administrations. Moreover, the application can be verified by the same remote party with a process called remote attestation. The advantages of FAIRY are summarized as follows. In terms of performance, we do not need further communication rounds beyond the total order broadcast that would be executed for the transaction in any case. We do not need threshold encryption operations which are expensive. We do not need the complex distributed key generation protocol to establish the key shares. Moreover, as we saw, we can validate the contents of our transaction before ordering and therefore prevent malicious clients from submitting garbage to the system. In terms of fairness, we guarantee both input causality and sender obfuscation. We guarantee fault tolerance against both Byzantine nodes and Byzantine clients. And in terms of modularity, our protocol is not only limited to STX, but to any trusted execution environment with the aforementioned properties. And in terms of total order broadcast, any total order broadcast protocol will do as an underlying protocol as long as it can provide a proof that some sequence number is added to a transaction, which is a pretty basic property. Our modular design is presented here in a bit more detail. Alice submits her encrypted transaction to the node, and the node forwards this transaction to the trusted execution environment, which decrypts its contents and validates it. By validating a transaction, in our implementation, we mean authenticating the client, but this can be extended to any application-specific validation of the transaction contents. For example, in our stock exchange service use case, we can check if Alice has enough funds to buy some stock. The trusted execution environment runs a process which is called trusted client proxy because this process, on behalf of the client, submits the encrypted transaction to total order broadcast. Then, total order broadcast is run seamlessly among the nodes as it would for any normal transaction by any client. It assigns a sequence number to the encrypted transaction and returns this with the proof that this sequence number was added to the transaction to the trusted client proxy. If this proof is validated, the trusted client proxy reveals the transaction back to the node, and now the transaction can be added to the ledger with a sequence number that it was initially added to the transaction by the total order broadcast protocol. Let us now examine in more detail the required setup so that the client can submit an encrypted request, which can only be decrypted inside the trusted execution environment. To do this efficiently, the client establishes a symmetric key with all trusted proxy clients. Each TPC is equipped with two public and private key pairs, one for encryption and one for signatures. And the client, as well as other nodes, can validate the public keys with the process of remote attestation. The client will use the encryption public key to submit an encrypted client registration. The client registration contains the symmetric key that the client will later use, a one-time identity, which we will see shortly how it is used, and the client uses a public key to sign the encrypted client registration transaction so that the trusted proxy client can authenticate that this comes from an authorized client. The trusted proxy client can use some public key infrastructure and a root certificate to ensure that the registration comes from an authorized client to the system. Once the encrypted client registration is submitted to the trusted proxy client, the trusted proxy client will create an association of this one-time ID with a symmetric key. Ferry for input causality needs to encrypt the payload of the transaction. To do this efficiently, as we said, we use the symmetric key that we established previously with the client registration. Then, once the client submits the request to the node, the trusted proxy client will create some request, which we call enclave request, and it is compatible with the underlying total order broadcast protocol, and will use the client request as payload to this request. This request is signed with the TPC public key for signatures, so that other nodes can authenticate that this request comes from an authorized trusted execution environment. Then, TPC invokes on behalf of the client total order broadcast. To further guarantee sender obfuscation, as we said, we need to hide any information pertaining to the client's identity, which would include, for example, the client public key that could be used to authenticate the client. Instead, we use authenticated encryption to authenticate the client with the symmetric key that we have established. However, now, if we submit a completely encrypted request to the trusted proxy client, we need some anchor to identify which key to use in order to decrypt and authenticate the contents of the encrypted client request. In order to achieve this, we cannot use the client identity inside the encrypted client request. Instead, we use a one-time client identifier. It is crucial that this identifier is a one-time identifier because we need to be able to not identify the request that the client sends some other time later using the same identifier. Instead, we will use another identifier for the next request, and we will put this identifier encrypted in the client request that the client submits. To anchor this, the first one-time identifier is encrypted inside the registration of the client, as we saw earlier. Further protocol details can be found in our paper. Now let's examine a bit our prototype and evaluation. Our prototype was implemented in Rust with Intel SGX, and we call FAIR-MIR our FAIR implementation on top of MIR BFT. Our experimental evaluation includes comparing FAIR-MIR to the underlying MIR BFT protocol, which is an efficient total order broadcast protocol. Moreover, we compare FAIR-MIR to the commit reveal scheme by Duan et al. Implemented on top of MIR BFT, which we call CR-MIR. We do not compare against the threshold encryption protocol, as the commit reveal scheme is much more efficient. We performed the experiment both in local area network and wide area networks to check performance, scalability, and limitations of trusted execution environments. We will now focus on the comparison to state-of-the-art and the underlying total order broadcast protocol. We will look at the latency throughput plot, which we'll create by increasing progressively the load in which we submit to the nodes for all protocols until we reach saturation. That is the point where throughput stops increasing and latency increases rapidly, indicating that the point just before saturation is the best performance that the system can achieve. We can see that FAIR-MIR adds a 20% overhead on top of the underlying total order broadcast protocol and maintains the same latency. This 20% overhead is the price we have to pay for adding fairness to the underlying total order broadcast protocol. However, FAIR-MIR achieves more than double the throughput of commit reveal MIR, as well as reduces its latency by half. This is an expected result if we consider that the commit reveal scheme runs 2 times total order broadcast per transaction. Moreover, to examine the scalability of our solution, we need to look into request disclosure phase. This is because request disclosure is the only phase which depends on the number of nodes in the system. This is because of the proof that needs to be validated at request disclosure. That could be, for example, signatures from all correct nodes. The more nodes, the more signatures a TPC needs to verify. Indeed, performance drops as the number of nodes increase. However, if we process more requests in the same block, that is, if we do some request batching, this cost is amortized, and the more requests we have in the block, the less performance drops by increasing the number of nodes in the system. If we reach a high number of batching, which is comparable to the batching done in the underlying protocol, we can see that the protocol scaled pretty good along with the underlying MIR BFT protocol. We invite you to read our paper in order to see a more detailed protocol description, more concrete theoretical background, and more experiments. We will be happy to address your questions in the comments below. Finally, to summarize, we saw that distributed ledgers or blockchains enable new decentralized services, where total order broadcast is a key technology. Fairness properties prevent front-running attacks, and we will require both input causality and sender obfuscation. FAIRY is a modular FTOB extension which we implemented with Intel SGX. It has small overhead, it achieves half latency and double throughput of state-of-the-art, and it is scalable with the underlying total order broadcast protocol. We thank you for your attention.